Hi, my name is Shriyat and my co-author is Dr. Appala. Our project is SeedAI, Sustainable Data and Energy Efficient AI Model Training Framework. We are an entry for the Outstanding Student Presentation Award. Introduction. Training modern AI models like large language models requires huge datasets and massive computational resources. Data centers already consume millions of kilowatts of electricity. This is around 1 to 2% of global electricity and emits roughly 190 million tons of carbon dioxide. Further, modern AI systems consume billions of gallons of water each year for cooling. The rapid growth of AI increases energy and resource demands, creating environmental challenges and emphasizing the need for sustainable and efficient AI solutions. There are three primary optimization techniques that are commonly used to improve the efficiency of AI systems. First, AI model optimization methods such as pruning reduce model size by removing redundant weights and lowering numerical precision. Second, hardware optimization uses GPU scheduling and specialized accelerators such as TPUs and AI chips to improve compute efficiency and reduce power usage. Third, dataset optimization utilizes methods such as stratified random sampling to reduce training dataset size while preserving representative information. Our project, SeedAI, focuses on data optimization for energy efficient AI. Related work. In dataset optimization, one common approach is random sampling or mini batch selection, where data is selected uniformly at random. While this method is simple and widely used, it does not preserve the underlying distribution of the dataset, which can lead to biased representations. Another approach is representative subset selection, which focuses on selecting samples that preserve the overall structure of the dataset. This helps to maintain data representations and improves training efficiency while using fewer samples. We combine stratified random sampling with a self-adaptive test framework for energy-efficient AI model training. Our method, the dataset is partitioned into groups known as strata, formed based on shared characteristics to preserve the original data distribution. Then, the samples are randomly selected from each strata, producing a smaller dataset that still maintains the original dataset distribution for model training. Next, the self-adaptive test framework ensures coverage of essential test cases through a feedback loop that updates scenarios based on new data distributions and observed outcomes. Finally, this results in a reduced dataset that maintains the distribution of the original dataset, reducing the training data set size for energy-efficient AI model training. Now, let's talk more about stratified random sampling. Stratified random sampling is a dataset selection technique where a large dataset is first divided into groups known as strata based on shared characteristics. Each of the strata represents a specific characteristic of the overall dataset. Then, samples are randomly selected from each strata to ensure every group is proportionally represented in the final dataset. This helps maintain the key features and balance of the original dataset while reducing its overall size. Next, the self-adaptive test framework is designed to ensure comprehensive coverage of essential test cases during dataset selection for model training. It begins with an automated analysis of requirements to identify all possible test scenarios needed for model evaluation. Then, a feedback loop is introduced that continuously evaluates new data and observed outcomes. Based on this feedback loop and the framework can add, remove, or modify test cases to better reflect changing data patterns and requirements. Finally, this adaptive process ensures that the selected dataset remains representative of required scenarios while continuously improving test coverage and leading to more efficient and robust AI model training. Next, experimental results. We compare the baseline model training approach with our optimized method across test runs ranging from 10 gigabytes to 10,000 gigabyte datasets. The experiments use public Hugging Face datasets for text and utilize the Microsoft Azure platform. The evaluation includes a baseline phase using full datasets and optimized phase using stratified random sampling with a self-adaptive test framework. The baseline requires higher GPU usage and longer processing time as the dataset size increases. In contrast, our optimized method reduces the dataset size while preserving key data characteristics. Across all test runs, it consistently reduces GPU usage by half while utilizing less processing time, achieving around 60 to 65% reduction in dataset size. Further, as the dataset size increases, our framework becomes more effective. For example, when the dataset size is 10 gigabytes, it's reduced to 4 gigabytes, and when it's 100 gigabytes, it's reduced to 38 gigabytes. Similarly, for a 10,000 gigabyte dataset, the optimized dataset is reduced to only 3,362 gigabytes, demonstrating strong scalability for large-scale AI model training, as the model optimization went from 60% to 62% to 66%. This shows that our method maintains model accuracy and performance while reducing dataset size by approximately 60 to 65%. In conclusion, modern LLMs use millions of kilowatt hours of electricity and billions of gallons of water for cooling. Our approach, SeedAI, combines stratified random sampling with a self-adaptive test framework for energy-efficient AI model training. This framework reduces the dataset size, GPU usage, and storage resources by approximately 60 to 65% while maintaining model accuracy and dataset representations. SeedAI demonstrates scalability and adaptability for LLM applications towards sustainable AI. Future work, we will plan to extend SeedAI into a larger scale and multimodal datasets, which include image, audio, and video data. We also aim to improve the self-adaptive test framework to support more complex scenarios and broader LLM and Gen AI applications. These are the key references for our project. Thank you for your time.